Today we're going to talk a little bit about the phenomenon of water bells. We're going to look at water bells from the perspective of an experiment done by G.I. Taylor in 1959. First, we're going to talk a little bit about G.I. Taylor as a person. He was a British physicist and mathematician, best known for his contributions to the field of fluid dynamics. He was born in 1886 and made his first notable contribution to physics as an undergrad at Trinity College in Cambridge through a paper on the interference of visible light. Throughout his career, he did work in a number of fields, including meteorology, mechanics of aircraft design, oceanography, solid mechanics of plastic deformation, propagation of blast waves for the Manhattan Project, and even work designing supersonic jets. It was actually only much later in his career that he did most of his work studying traditional fluid dynamics in a lab setting. By the time he wrote his 1959 paper on the phenomenon of water bells, he had actually already retired. The water bells paper was based off of a 1952 paper by F.L. Hopwood that showed a way to make water bells by flowing water through a thin slit. A couple other authors were also able to recreate the phenomenon, but none were able to come up with an analytical solution to describe the shape of the bell. From what we have found, it looks like the only motivation for the research was to increase the knowledge base on fluid dynamics, and there seem to be no direct connections to uses of water bells in technology besides the simple one, which is fountains. Results from the paper Taylor were able to find were actually an analytical solution. What he did differently, though, was that he flipped the setup sideways so the bell was formed horizontally rather than vertically, mitigating the force of gravity. He also created a flow around a cone with a known angle to create the bell rather than using a thin slit. This image is one of the images that Taylor was able to create of its water bells. You can see the stream starts here on the left and flows over the conical ending of a skinny tube in the middle, creating this really clean water bell. To quantify these shapes, Taylor plotted the curves based on the cosine of the interior angle of the cone. The thick lines show different bell profiles for cones with different angles. The dotted line shows the maximum radii for each meridian section. What we can see is that the bells start out short and skinny, and as the angle of the cone increases, they get taller and wider, until about x equals 0.65, when the bells start to stretch out and they get taller and skinnier. What's interesting about this is that there is a maximum length that the water bells in this scenario could be, no matter the cone angle.
So now we're going to get into the math of the experiment. Taylor actually uses a lot of variables, specifically there's 11 listed here, to explain the phenomenon, but as you'll see later that we don't really care about most of them, and only really one of them, which is the vertical angle, which is phi naught. Looking into the equations that Taylor uses, we should first understand the assumptions he made to get to the final equations. One of them is that the surface tension is constant. This allows him to remove T from all equations. Next, he assumes that viscosity and gravity are negligible. This was one of the biggest assumptions he made that differentiated his papers from others. Many experiments prior to his did not neglect gravity. Lastly, this is less of an assumption but more of a variable assignment, but the bell-shaped seat is projected in the form of a thin wall cone of semi-vertical angle represented by the variable phi. This is, again, the most important variable that we focused on. So in order to replicate his experiment, this variable was crucial for our calculations. Some of the equations that were in the paper but we did not think were beneficial for our equation are shown on this slide. The equations include the equation for fluid velocity, the equation for the balance of inertia at right angles to the stream, and the equation of continuity. These equations were simplified into two physical parameters, alpha and beta, which are highlighted. Ultimately, we didn't use any of these equations and solely used equations that depended on phi. This slide shows the equations that we used. By knowing phi, which is the vertical angle of the cone, we were able to calculate the trajectory of the bell as well as the locus of the maximum radius for each bell shape. But another important variable that Taylor neglected to discuss in the paper is Q. He mentioned some flow rate principles, but we realized during our experiment how crucial the flow rate was to create a good water bell. During our experiments, we found that if it is too high or too low, the water bell does not form. When the flow rate is too low, the water clumps together and flows below the cone. While when the flow rate is too high, the sheet that was formed was more spread out and less curved than the intended bell shape. From experimentation, we also found that different cone sizes also required varying amounts of water to achieve the water bell formation. We were able to calculate various flow rates, and we'll discuss this at a later point.
One of the most important factors to the success of our experiment is creating small diameter laminar flow onto the cones. Water straight out of the faucet has some turbulence and an uncontrollable diameter, so we made a nozzle to control and direct the flow. The nozzle is filled with straws parallel to the axis, which are held in place by a sheet of wire mesh. The straws direct the flow out of the nozzle through an 1/8 inch hole. To make cones in various angles so that we could test various water bells, we 3D printed 1-inch diameter cones and only varied the phi, the angle between the cone edge and its vertical axis. A stem on each cone allowed it to interface with the rig we designed to hold it coaxially with the nozzle. Here are the cones we used with stems removed. To set up our experiment, we aligned our nozzle and cone coaxially in front of a grid of 1 centimeter squares, with the nozzle tip about a centimeter from the cone tip. A valve on the hose going into the nozzle allowed us to adjust the flow rate for an ideal water bell.
To get our experimental data, we adjusted the flow from the nozzle using a valve until a water bell formed, which we then started recording. The following videos showed a different water bells formed at 30, 45, and 75 degrees. So, using the same flow that we would get making the water bell, we would measure the time that it took to fill a 1-quart bucket. This way we could get the time it took and a volume in order to get a flow rate. Then we would lower the flow using the valve until both lower and raise it to the point where a water bell barely formed, and then measure it again, measure the time again to get a minimum and maximum flow rate. This graph here shows the different ranges, with the horizontal line being the optimal water bell flow. It is interesting that even with this slightly wide range for different angles, one could use a flow rate of 0.03 liters per second and form a water bell for all of them. This next graphic here is Taylor's findings with an overlay from the results of our MATLAB model to predict the curves. You might want to note that although for different angles, you can see that our MATLAB model very accurately predicts the curves on this line here. And the calculated trajectories were then overlaid on some of our results from the video. For a 30-degree angle, it was a little bit off, but that's okay. Here we can see as they get to the higher degree angles, our model very quite accurately predicts the curves that the water bells form. And this is at 75 degrees.
Overall, we were pretty excited to get bells that match up so closely with the model. On the whole, we saw the same trends in how the bells change shape based on the cone angle as Taylor, but because we disregarded parts of the equations, the form was not entirely perfect every time.